Hello folks, my name is Dr. Zachariah Hildenbrand. I'm here with my colleague Dr. Kevin Shug, and we are the Collaborative Laboratories for Environmental Analysis and Remediation at the University of Texas at Arlington. We're coming to you from the Responsible Shale Energy Extraction Conference, which is a very unique event bringing together scientists, concerned citizens, operators, regulators, and technology companies to have an honest series of conversations about environmental stewardship in shale energy.
We'd really like to thank the support of the Cynthia and George Mitchell Foundation and Earth Day Texas for allowing us to put on this event. We believe that this content that we're going to be providing to those who haven't been able to attend is going to help answer and educate a lot of questions surrounding responsible shale energy extraction. So we hope you enjoy the content.
Going to be a very unique aspect of this conference. We're going to start talking about some of the new technologies, some of these innovative companies that are looking at problems, issues in unconventional oil and gas development, and developing technologies for us to address these. So it is a tremendous pleasure to introduce Coleen Gosse, all the way from Atlantic Canada. They have their own time zone out there. She is with Eosense. And us at Clear, we've had the tremendous pleasure of working with Eosense and some of their remote methane censoring technologies. In my opinion, they are one of the best companies out there in looking at this methane issue, because myself, I can't be out in the field 24/7. Our people on our team can't be out there 24/7 traveling. But if we have technology such as the one that Eosense is developing here, we can have an ally out in the field reporting data. And we first started with Eosense, and they developed a methane sensor for groundwater. We used it in areas where the water actually has so much methane in it, it's flammable, if you can believe that. And the thought is that you can put on this methane sensor, you can monitor fluctuations, increases in concentration. That information can go directly to the cloud. And if we have a lot of these sensors out into the field, we can have people putting information out into the cloud, and we can have concerned citizens, citizen scientists, and academics looking at that data to look at fluctuations and patterns. They brought one of their technologies here today. I believe this is a methane soil flux sensor. And so without further ado, all the way from Atlantic Canada, Eosense, she got her degrees from McGill University, which is the premier institution in Canada. Being Canadian, I can tell you, if you don't get into McGill, you're forced to go play college golf down in Texas, so that's what I had to do. So again, let's give her a warm round of applause for Coleen from Eosense.
Thank you, Zach. I'm super excited to be here. Firstly, because it's actually snowing at home right now, so it's really nice to be in Texas. And I'm also really excited to be at this conference. It's been really interesting to hear all of these different perspectives coming together, and I think where we sort of fit into all of this is something that everybody needs, all pieces of these puzzles. Everybody needs really good quality data to make decisions. So I'm going to talk a little bit about some of what I've been working on at Eosense. So I'm from Eosense is a company that makes instruments that measure environmental gases. So what do you do when you need to measure something that's really difficult to measure? Well, in the case of my colleagues, that meant finding a whole new way to measure what they were looking for. So they were measuring carbon dioxide flux, and they wanted to measure it year-round, including winter, and in Canada, that means a lot of snow. So most of the conventional methods aren't well suited for this. So they came up with something called forced diffusion, which I'll get into shortly, but it meant that they could measure soil gas flux everywhere from the Canadian Arctic to Antarctica and almost everywhere in between. So this is a picture of a carbon dioxide FD deployed in the snow. So the FD is a novel method of continuously measuring carbon dioxide flux. It uses a passive membrane to regulate the flow of gases rather than a pump. So that means it uses much less power, it's incredibly weatherproof, and it allows for the direct measurement of flux. It's fully automated and self-contained, and what I've been doing is trying to modify this forced diffusion technology, which has been established for carbon dioxide, to adapt that to measure methane and to look at other gases like VOCs and potentially H2S. So this is the Methane FD, so it's a little shorter and stubbier than its carbon dioxide sister. And basically you can set it up. We've got a battery that can fit in this little box, and you can hook it up with a solar panel, and you set it up and you leave it there, and it will directly measure flux continuously. And this is, just for comparison, a picture of one of the conventional chamber methods for measuring flux right next to an FD. So it's a little more cumbersome. There are a lot of moving parts, and that actually hooks up to another analyzer. And why do we care about continuous measurement? Well, it's really important when we're looking at emissions. A lot of the conventional methods, they'll only look at a short half an hour of time during a day. And we know that flux varies a lot due to different factors like precipitation, pressure, temperature, and those vary quite a bit during the day. So if you're only looking at half an hour of time, you're not getting a good picture of what the real flux looks like during a day, a week, a month. So this allows you to be able to detect but also quantify a leak. You can have a high sampling frequency, and looking at continuous data allows you to identify anomalies and sort of separate those from what is the actual flux in the area. A lot of times there could be a leak, but it's a slow leak that maybe you can't detect with a handheld sensor. Or the flip side of that, you could detect a really high concentration, but it could be a naturally occurring event and not actually a leak. So being able to quantify what the real emissions are is really important and really valuable. And another interesting way to collect the data would be to have a network of FDs collecting baseline data, and you'd have the ability to correlate what different FDs are saying and match them to different activities happening in the area. It's also really good for decision support. So something that I'll be looking at with the methane FD is looking at the ratios between different gases to help identify the source of a gas being detected. As we know, methane, for example, can come from several different sources. We know could be related to gas migration, but there's also naturally occurring methane due to bacterial activity. So being able to differentiate between different types of gases will be really useful. So that's something else I'm looking at. And having this on-the-ground direct flux measurement is really useful for vetting and ground truthing top-down approaches to measuring methane emissions. So I'll skip over this, but if anybody is interested in talking to me more about this, we did do a controlled leak study in Nova Scotia in November. So you can see from the pictures, the FDs were quite a bit taller than it is now, and that was one really neat thing to come out of this study was that we discovered that a small, low-cost sensor worked just as effectively as a much larger one. So in this iteration of the design, we took out the big sensor, so it's much smaller. So I'd be happy to talk to anyone about our leak study afterwards. We also did a study in California last month looking at abandoned oil and gas infrastructure. So we were looking at wells. So there was a well that was decommissioned about 15 years ago, and we were looking to see if it was leaking. So we're still analyzing that data right now, and this week my colleague is testing some devices at a landfill, so looking at methane emissions from a landfill. Eosense has a couple of other instruments that also measure flux. They're a little more conventional, but we have an auto chamber, which is one of those accumulation chambers like I showed you before, but that would need to be hooked up to a separate analyzer. We have a GP, which is a gas probe, so that's a concentration measurement device. And then we have a more portable multiplexer, which allows up to 12 of the auto chambers to be connected together. So what's next for this project? Well, it's super exciting. What I'm looking at right now is creating a stable sensor environment, which will allow us to use low-cost sensors, to have several of them in one place, and that will really improve our ability to look at gas identification. We're hoping to develop this into something that's really low cost, and that would allow for a network of these instruments to be deployed. So thank you very much. I'd be happy to chat with anyone if you want to talk about methane. I'm super excited about this project, super interested in learning more about methane and what everybody else is working on. Thank you very much.
Outstanding. So again, the Eosense, Coleen has to be commended for coming out here, showing off the technology. So often in the tech world today, it's all about how much money have you raised in venture capital on an idea, and here's a company that actually has an innovative product that can go out into the field. So it's really quite impressive. Coleen, are there ecological effects of having methane in soil? Is that a good thing? Is it a bad thing? What's the story?
That's a great question. That's a really good question, and I'm maybe not the best person to answer it. I have seen evidence at a well that had a really, what I think was a really slow leak, and we saw a high amount of microbial activity, and so it was. We knew this well was leaking, but we saw a decrease in the methane concentration around the well and an increase in the amount of CO2 being produced because the microbes were degrading the methane and releasing CO2.
No, and that's an incredibly important point. We're actually going to hear a presentation from Dr. Inés Santos about how methane can actually attract pathogenic bacteria into the environment, which we do not want. So you talked about the device being user-friendly. I can see my mom going out there implementing this technology and tweeting to her friends, hey, you know, I've got methane in my soil, which is great. What kind of costs are we looking at for a device like this?
That's another great question. So we're obviously still in the field testing phase of things. So we don't have a cost right now. It'll depend on what sensors we put inside, and maybe that will be customizable. I can tell you that the carbon dioxide CO2 sensor that we do sell right now is in the 5K range, and I'm sure we'd love to be in that same range for this guy, but I can't say right now exactly.
All right. Well, as scientists, we get very excited when we get new toys and implement them, and I get really excited when I don't have to travel all across the country to collect samples, and I can have the robots do it for me. So let's give her a round of applause. Thank you.
I forgot to mention, but this stable sensor environment that we're looking at will hopefully be able to be implemented in something, an improved version of our groundwater sampler. So there's a lot of really cool stuff happening right now.
Excellent. Thank you very much.